Okay guys, so now we're going to just look at this very important thing called a haloform. Okay, so basically you guys have heard of it: chloroform, bromoform and iodoform. They are the form CHX3, where X can be chlorine, bromine or iodine, right? This is nothing new. Where is this formed? The most often place where this is formed is if I have, say, an aldehyde or a ketone, right? The only important thing is that I should have a methyl. So basically a methyl or methyl, and you should have, say, an aldehyde or a ketone or something. Okay. For example, if I have a methyl ketone, something like this, I can form a haloform with this. Okay. If I have say, this is CH3, CH2, CHO, right? This is propanal. This will not give us the required haloform. Okay, and you will see why. Ethanol will give us required haloform. Okay, so which means if I have any alcohol, such that I have an alpha hydrogen, okay, and a methyl group, any alcohol of this form will answer the haloform test. Now I am going on and on about haloform test without telling you what the haloform test is. The haloform test is a set of chemical reactions which results in the formation of a haloform. Okay, and we generally talk about iodoform because iodoform is a yellow precipitate. Okay, this is a yellow precipitate, while chloroform and bromoform are both colorless liquids. Okay, so we can generally, if iodoform is formed, we will know because you will see a yellow precipitate in the test tube. Okay. So our job is to find compounds such that when I add iodine in the presence of a base, I end up with iodoform CH3. Okay. So and I'm telling you beforehand that these are the substances which answer. If I have a methyl, right, beside, say, a carbon which has either a double bond O and whatever it wants here, it can be a hydrogen or whatever, or you want a methyl, a hydrogen, and anything you want here. Okay, so that's the deal. So any compound of these two forms will answer this test, and you will see exactly why any compound of these two forms will answer the test. Okay, just in a minute. So remember, we have a methyl, a carbon, double bond O with anything, or a methyl, a carbon, a H and OH with anything. Okay. The pretext is that if you have an H and an OH, it will always get oxidized to this type of a form. So these two will go, this bond will come here. So this get oxidized to this, and you will be left with one carbon remaining. So that's basically the idea here. Okay. So once again, I'll reiterate myself. Any substance, any compound of the form methyl must be present, a carbon, a double bond O, and anything you want, or a methyl along with a carbon, an OH, and an H. Because these two together can get oxidized to double bond O along with anything else I want. Okay, so these two are what we call the compounds which answer the iodoform test. Okay, now let me tell you how the iodoform test works, and you will see why a methyl is absolutely necessary for this. Okay, so let's discuss now. But in the whole board, let me take first an answering substance. For example, let me take acetone, okay? Or in fact, let me even take better, let me take ethanol. CH, in fact, let me say this side. So I write C double bond O, H, C, H2, and then put an H here. Okay? And the job is to add iodine in the presence of hydroxide. Okay? If we do that, we have to track how the reaction proceeds now. So let us first say you add, so let's see how the reaction moves now. The first hydroxide ion, right, you're going to have one OH minus. I'll put a tabular column here, okay, where we track how much we've used and how much we've gained. So this is for reactants, this is for products, okay. Let's see how much. We are going to use one acetone, right? So reactants, we have used one acetone so far. This is for balancing purposes, okay. And in reactants, we have used one OH minus, okay, so far. Now the claim is OH minus great base, right, is going to eat up this proton. This hydrogen is going to go. And they are going to form water together, right? So till now we have one water. But so this is basically like saying minus H plus, right? So if you lose minus H plus, this bond, this hydrogen goes away. So this bond is with the carbon, right? Which means carbon gets a negative charge now. And this negative charge is well stabilized and all, because you can see that it's well stabilized because of resonance, right? With double bond and stuff. Which immediately actually tells you, gives you one reason as to why you need a methyl. Because suppose this was something like this, right? CH2, CH3, then see primary carbanions are much more stable. So you will not get a minus here, you get a minus here. But if you get a minus here, so CH2 minus you get, right? This is not stabilized by resonance. So you need the carbon immediately adjacent to the carbon containing double bond to have a negative charge, and that is only possible if you have a methyl group. Or else it will be a carbon which is secondary or tertiary, but that is highly unstable for a carbanion. So this is one of the reasons. It's not a very big reason, but just when you start, you're able to see it. So I'm just telling you, okay? You have this substance now. Now, what's it going to do is, remember we had iodine in the solution, right? So we're going to draw this like this. What's going to happen is that iodine, the bond is already pretty weak, okay? This guy recognizes it and he plants his electrons on top of iodine. Iodine can only have valency 1, so these bonds are shifted here. So I have a free I minus in solution, right? This I minus goes away, so I am left with products 1 I minus. Okay, so what am I left with? The CH2 and I form a bond, right? So I have CH2I plus I minus. Now I take another OH minus, okay? So now I have made this 2, right? Same step comes, takes away a hydrogen. Minus H plus, you get water. So this becomes 2 water. What do? I get a negative charge now, again on the carbon. I take another iodine molecule. So I have to, I forgot to track the iodine. So now I have used 2 iodine molecules. Okay, this is the second one. I forgot to put the first one in, sorry about that. Again, same logic. Negative charge, blocks its electrons on top of this guy. This guy shifts. What am I left with? I'm left with another I minus in solution. So this doubles. And I'm left with this compound now, right? CHI2. Then what do? I do the same thing again. So now what I'm going to do is I am going to look at this and say, okay, take another OH minus. So now my reactant side is become 3 OH minus, right? It's going to take up a hydrogen H plus. I'm going to get Ci2 minus. H and OH minus are going to give me water. So this again becomes 3. I'm going to take another iodine molecule. So this becomes 3. Right? This guy is going to attack. This guy is going to leave. I get one more I minus in solution. Right? And I am left with this compound. Ci3. Right? Now what happens is, I am going to take one more OH minus. Okay, so now this equals 4. Right? Now I have no more acidic hydrogen. So what's next best for a nucleophile likes to be a base first and then a nucleophile, right? So it then sees, okay, so this double bond O, see the carbon atom is highly electron deficient. Okay, you gotta remember that. C double bond O something. This guy is always pulling electrons downwards, so this guy always has a delta positive. So most reactions you will see in aldehyde chapter will be, the first step will be nucleophile attacking the carbonyl carbon atom. It always happens. Okay? So what happens is, nucleophile attacks here, right? And the carbon has 5, it doesn't know what to do. It has to break one of these bonds. Breaking this bond doesn't seem, it's futile, right? Nothing's going to happen, no minus, it's not going to help. But I can break this bond. And you will see why I can break this bond in a minute. But generally, historically or in the molecule, what happens is, first this bond breaks, then the molecule says, oh wait, I don't want that one to break, so it will come back, and then this bond will break. Because the pi bond is weaker, right? So the molecule says, okay, I'll give the pi bond first, it lets the pi bond go and then says, oh man, this doesn't feel good. So then brings the pi bond back and then part with this bond, okay? That's what generally happens. You represent it like this, But for you guys, since you guys are just starting out, I just started to put this one. Okay. So anyways, what am I left with now? I am left with CH double bond O and then OH, right? And I am left with the CI3 minus, right? And what is going to happen now? There are plenty of in fact, this is a base, right? And this is an acid. So they will exchange. They will do neutralization reaction here. Proton will get exchanged, and you will get what? Finally, you will get HCOO minus plus CHI3. Okay, and this is a precipitate. We draw the down arrow, and so we can update our product side, right? So we got what? One HCOO minus, one of them, and one CHI3. Okay, but notice that we've written all these in terms of bonds. So let's try to write them. Let's try to we've written all this in terms of ions, right? But as we said, ions are self-confidence issues. So let's try to make the whole thing nice. Okay, so let me write my balanced equation now. Acetone plus 4 OH minus. I'll keep doing that for now. This stock isn't that good. Plus 3 iodine will give me 3 water plus 3 I minus plus HCOO minus plus CHI3 precipitate. Right? This much is clear? Now we do not want ions hanging around, so just to make the equation to finish, because I don't want to pour a bottle of OH minus, right? I can only pour a bottle of NaOH. So what do? I add, see, I want to make this NaOH, right? I have 4 OH minus, so now suddenly I try to add 4 Na plus, right? And if I add 4 Na plus on this side, I have to add 4 Na plus on this side, right? The rule of nature. So 4 Na plus. 4 Na plus and 4 OH minus, this guy becomes 4 NaOH, right? You have 3 I minus. If I write this as 3 Na plus, and then I put the other Na plus here, right? Then 3 I minus plus 3 Na plus will give me 3 NaI, right? So we get 3 NaI. And Na plus HCOO minus using sodium formate, right? So sodium formate. HC. So this is the basis of the haloform reaction. What I just written is a balanced form of a haloform reaction. If, however, see now you guys understand why you need the CH3, because the CH3 here is what becomes CH2I, CHI2 and CI3 minus, right? If I have CH2 or something, it will never do that. So to get the haloform in the first place, I need only one carbon here. So I do need a methyl here. Okay? In fact, we can generalize this by putting an R here. Right? If so we can generalize this by putting a R, right? So CO, I'm sorry, we should have gotten CH3. I made a mistake when I was writing. If you put R here, generally the proposition is that you get RCO, RCO Na. That is the proposition, okay? And that balances it out itself also. I made a mistake somewhere in the middle, so let's just retrace the mistake. The place where I made a mistake is this. So I think I just wrote the thing wrong. So we took acetone, right? Another name. So we took C double bond O, CH3, right? And we took this CH3 on this side, which was basically became CI3. And the OH minus attacked. This bond shifted, came back, and this bond broke, right? So I was writing CH3COOH. Okay, so that's a mistake I made. Sorry about that. But the general reaction, we're ready to write the general reaction. See, this is an example which shows that how mechanism can help you balance without you breaking your head with the math. Okay. So if you have to write the reaction is RC double bond O, the methyl always, plus 4NaOH plus 3C. This can be generalized to any halogen. So plus 3X2 will give me 1 CHX3. Precipitate if it's an iodide plus RCOONA plus, what is this remaining? RCOONA plus 3H2O plus 3NA. So this is the haloform reaction for any halogen. So the problem now is your book tries to overcomplicate it. Okay. So what your book thinks is that they don't want to explain this part. Okay. So they explain this in different in like 5 different reactions separately. So they first do CH3CO. Sorry, they do CH3CO, CH3. Then they do acetone. Instead of acetone, they do acetaldehyde. Instead of acetaldehyde, they do ethanol. But so let me just show you this one thing, and then I think everything else will be pretty simple. So once you have understood this very clearly, I suggest you actually write it down once and see how the reaction goes for yourself with the balancing table also. That table is important. But now you've done that, you can look at ethanol, right? So I told you that if you have any R, a C, you need an H, OH, and a methyl, right? This is the job. Because this guy will get oxidized to RCCH3 double bond. And this is the guy we want. And you know that if you do haloform on this guy, you're going to get whatever. You do plus 4NaOH and 3X2. You're going to get the same products, right? 3 water, 3 NaX, 1 RCONA, and 1 CHX3. So that's how this is going to be. Okay, so you guys want to remember that. This oxidation happens because of the, so basically, this you should have learned in 11th. Iodine in the presence of OH minus likes to do a weird thing. Okay, so it does this. So you can see that the iodine, which is at a 0 oxidation state, has become a -1 oxidation state and a +1 oxidation state. This is for weak acid. For weak base, if you are a concentrated base, you will get I- plus IO3 minus. Anyways, what happens here is basically this is called disproportionation. Okay, so this IO minus happens to be a good oxidizing agent. So the oxidizing agent will oxidize this guy to this guy. Okay, so that's about it. In your book, once they have discussed the formation of it, they discussed the plethora of reactions which these guys follow. Okay. And the only important reaction you need to know from that is what we call the carbylamine reaction. Okay, and I really love to write the mechanism of the carbylamine reaction for you guys, but frankly, it's just too long. Okay, and my board won't fit it, and you guys don't need it to be honest. So let's just exempt from any mechanisms. Okay, worst case, I'll send you guys a video or something. The carbylamine reaction is historically done using chloroform, not hydroform. Right? It goes like this. So R, NH2, any primary amine, that's the category here. Primary amine. A primary amine is one which has an NH2 group. Okay? This is the secondary amine. This is the secondary amine. Okay? And tertiary amine, if I use this is it. Right? So primary amine is something which has a nice NH2 with it. So any primary amine on reaction with chloroform and KOH will give me KCl plus H2O plus R. This is the other way to write the isocyanide, but you can always write it in whatever you want. So you can write it like this, and you know, whatever, up to you. But that's basically the deal. Okay. So you get R and C. The convention is written like this. We talked about another way to write it in the other thing. So I'm not going to put the short now. But this is basically it. Okay. So this is the reaction. If you have to balance it, just remember you put a 3 KCl, 3 H2O, and balance it from that. You just remember these two are pretty much done. Does it balance from here? You have an R, that's balanced. Okay. Chlorine is balanced. That's good. Potassium is not balanced, so you need to put a 3 here. Now potassium gets balanced. What else is remaining? The hydrogens. So let's hope the hydrogens balance each other out. You got 3 plus 6 hydrogens here. You have 3 hydrogens, 2 hydrogens, and 1 hydrogen. So 6 hydrogens. So I think you're done, right? 3 oxygens, 3 oxygens. So you're done. Just remember the number 3 for this reaction, okay? And put it 3 KCl, 3 H2O, 3 KOH. Just remember that. This is a famous reaction. It's used for for example, if I have say aniline, right? And say benzylamine, which is basically let me here's the board for you guys. I think it's not getting legible. Oops. Now, let us go simple first. If you had, say, CH3 NH2 versus CH3 and CH3 H. They ask you, give a chemical test to distinguish. Carbylamine is the way to go. Let's give an answer. How do you, by the way, how do you find out what's the characteristic of this isocyanate? Is that it has a very bad smell. Okay, so it smells super bad. It's I believe the actual word for it is offensive odor. So offensive odor. In fact, I think you might you're not allowed to do this test in your practical exam. But I think if you want, you can ask your teachers to do it maybe once or something very safely. So it has an offensive odor. So that's basically the deal. We talked about how the iodoform test works. The iodoform test works like this. So we said that any compound of the form or any compound can be oxidized to that form. For example, this, right? With anything here, right? Y means anything. Can answer the iodoform test, right? So the conjecture will then be that if I suppose have ethanol, right? CH3 C H H. This is ethanol, right? Ethanol satisfies the condition of this, right? But methanol does not. Methanol has this. This is methanol. So someone asks you, give me a chemical test to distinguish ethanol and methanol. You will say iodoform test. This guy answers because he has a methyl group, right? That's another thing. Also, see, this is where mechanism will help you a lot more. So remember in the mechanism, one step in, right? What is the product? What is the compound we had? The compound we had in our hands was R C double bond O CH2X, right? And from here only, so the first step ended with this, and then all the other steps continue, right? Which means if I have this guy should also satisfy the Haloform test, right? Except for the fact that he used 1 less mole of all these guys. He used 1 less mole of OH minus, 1 less mole of iodine. So this guy satisfies iodoform test. This guy satisfies iodoform test. And even this guy satisfies iodoform test. Right? So all of these guys satisfy the iodoform test. So iodoform, so that's something you want to keep in mind. Some other reactions are there in your book. Okay. This is basically the basics of the iodoform reactions. Okay. Other reactions are generally not asked. They are just the word is miscellaneous. Okay. So they're interesting to learn, but not asked much. So I'm going to leave you guys to read up with that. Okay. Read up on that. It's kind of interesting, but don't spend more than say half an hour on that stuff because it's not going to. The probability that will come is slightly lesser than any of this hardcore theory stuff. Okay. So with that, I am glad to announce that we are finally done with haloalkanes and haloarenes. We will do the question set. The question set that I have sent to you contains part A and part B, and you will be interested to know that part A is actually the UT paper on haloalkanes from when I wrote the UT when I was in 12th grade. So that was my UT1 paper. Okay. So we will solve that paper. It's not fully there. Meena Ashimam actually she had to go through quite some struggle to find that paper. She wrote the last part with her hand, so that was not there. But the PDF has everything else. Okay, so we'll do all the other questions. And part B was formulated by me, so it also has some other extra questions. if you guys don't have much time, just attend this part, because this part is what is probably resemble the questions which are coming for your test. Okay, so that's all I can think of. I can't think of anything else. I will be sending you guys pictures of my notes also along with this. So it's been good to teach you guys. Take care. So I'll see you in the question set answers, right? When you see the question set, try to solve them after you watch these videos first, and then use my answer videos to just check your solutions. Okay, it will help you much more than actually just watching me solve the questions. So see you guys in the next one.